So this is going to be commentary of my going over the solutions to problems that students were recently given as review for the impulse and momentum unit. So the first problem, we had a weasel running toward the right colliding with a chicken running toward the left, and during the collision the weasel grabs the chicken and the chicken-weasel system comes to rest. So the question is, what was the total momentum of the system before the collision? So the answer on this is that the total momentum of the system before the collision was 0. Because if the weasel chicken system came to rest after the collision, that means that the total momentum after the collision must have been 0, which means by conservation of momentum, which says that total momentum before equals total momentum after, the total momentum of the system before the collision must have also been 0. So in the next problem, we have another weasel, in this case of a smaller mass running toward the right and colliding with a chicken of mass 3m that was running toward the left. And during the collision, when the weasel grabs the chicken again, and the weasel chicken system comes to rest. So this time the question is, before the collision, which of the following is true? Was the weasel running faster than the chicken? Was the chicken running faster than the weasel? Were they running at the same speed? Or is there just not enough information to figure out what was going on? So in this case, again, the total momentum after the collision is 0, which means the total momentum before the collision must have been 0 as well. But remember, momentum is mass times velocity, and this chicken has a mass 3 times the mass of the weasel, which means the chicken must have had a velocity 1/3 the velocity of the weasel in order to cancel out the weasel's momentum going the opposite direction, so the total momentum is 0. So the weasel must have been running faster than the chicken, 3 times faster in fact. So in the next situation, we have a 90-kilogram man wearing ice skates and at rest on a flat, frictionless pond. It's nice how we have all kinds of frictionless surfaces in physics. The man is holding a 5-kilogram bowling ball. We are not going to speculate how this man got onto the frictionless pond to begin with, or came to rest afterward, but anyway, maybe he was dropped there. So if he rolls the ball toward the left at 9 meters per second, what will happen to the man? So the answer to this is that the man is going to slide toward the right at 0.5 meters per second. So let's see how we got there. This actually requires a calculation. So we start off writing our givens down like good physics students, with our masses, our initial velocities. Our final velocity is the one that is unknown, so we designate it with a question mark. And the final velocity of the thrown object is 9 meters per second, opposite to the man. So we use conservation of momentum. And since everything was initially at rest, we have that the left side of this is 0. Of course, the right side is 0 as well, but that doesn't help us because the stuff that we're trying to figure out is embedded in the right side of the equation. So calling this 0 wouldn't really help us. Just taking the expression and setting it equal to 0 and then solving is what is going to help us here, because each of those momenta is a mass times a velocity. So we first isolate the side. This final one velocity at v1 final is over here, so we want to get this side by itself first. So I just subtracted the m2 v2f from both sides and then flipped the equation around, because I kind of like always having the variable I'm looking for on my left, but I'm also allergic to minus signs. So I then divide both sides by the mass 1 because I'm trying to get v1f by itself. And now it's time to plug in numbers. And when we plug in our numbers, we get a speed of plus 0.5 meters per second. So now, in our next problem, we have a 3-kilogram cart moving at velocity 20 meters per second, colliding with a stationary 5-kilogram cart. And after the collision, the second cart has a velocity of 14 meters per second. So the question is, what is the magnitude and direction of the velocity of the first cart now? So we're going to assume that all of this is going toward the right, and I was a bad physics teacher. I didn't put my plus signs on my initial and final velocities and everything, but we're going to assume everything's going toward the right. And we're trying to find this unknown final velocity of the first cart. So there's where we stand so far. Again, conservation of momentum. And what does that mean? Well, There are two objects in, and there are two objects out. So each one of those has a momentum. So P1 initial plus P2 initial, that's what sum of P initial means. Sum of P final, well, there are two objects going out, so that would be P1 final plus P2 final, one for each of the objects. And each of these P's becomes an MV, but one of them is 0 because we notice that the initial velocity of cart 2 is 0, so that must mean that the momentum is 0 as well. If it's not moving, it has no momentum. So now, again, we're looking for the final velocity of cart 1, so we want to isolate for that. So what we're going to do is we're going to subtract this m2 v2f from both sides, and then we're going to divide both sides by m1. So the next step, dividing both sides by m1. And in this case, I decided to separate my fraction out. So in other words, m1 v1i over m1 is just v1i minus m2 v2f over m1. So that ends up over here. It just makes it a little easier to plug in the numbers and cancel the units, and also a little easier to see what's going on. In other words, this final velocity has something to do with the initial velocity and the change in velocity that occurred due to the collision. So now we plug in our numbers, and as a result, we get negative 3.33 meters per second, which means it's going at 3.33 meters per second toward the left. That is how we write our final answer. So next, we have a situation that is pretty much identical to what we had with the man on the frozen pond. We have, in this case, a 1-gram bullet fired horizontally from a 2-kilogram rifle that's hanging from a string. So the question is, what's the magnitude and direction of the rifle's velocity just after it's fired? Obviously not a long time after, because a long time after it's going to end up going up on the string. In fact, we could turn that into a conservation of energy problem if we wanted to figure out how high it will go. But right now, we just care about what is the rifle's velocity at the instant after the firing of the bullet. So we'll let object 1 be the rifle and object 2 be the bullet. So there are our givens, and we have conservation of momentum. Surprise, surprise. So initially, everything is 0 because nothing's moving. So question is, well, turn that 0 into P1 final plus P2 final, and each one of those P's is an MV with appropriate subscripts. Notice that I included 2 steps on the same line. That is okay, especially if you're trying to save space in a PowerPoint slide. So moving things around, we are trying to find our V1 final, so I subtracted M2 V2F from both sides, and actually I subtracted M1 V1F from both sides, and then I got rid of that minus sign by dividing both sides by negative M1 to get V1 final by itself. And now it's time to plug in our numbers, and when you do that, you get negative 0.5 meters per second. So we say that the rifle's recoil velocity is 0.5 meters per second opposite to the direction in which the bullet was shot. Magnitude and direction. It's a vector. Velocity is a vector. So in our next situation, we have 10-kilogram object going to the right, and it's going to collide with a second object that is initially stationary. But this time, we don't know the mass of the second object. We're going to say the second object ends up springing off toward the right at 2 meters per second, and the first object goes backward at a speed of 2 meters per second. And what's the final mass? Or I shouldn't say what's the final mass, but what is the unknown mass? So we're still going to use the technique of energy conservation. So here's where we're at so far. There's our energy conservation. That should look familiar. And 2 objects in, 2 objects out. So each sum of P is a P1 plus P2 with the initial or final subscript. And each one of those P's is an MV. But again, the unknown object's mass, the object with the unknown mass, it's initially not moving. So at least we know its momentum. It's initially 0. But we're still looking for that unknown M2. So we rearrange, and we're solving for M2. There we go. So there's where we're at so far, and we're going to make this look nice and pretty. We're actually going to factor out an M1 so it looks a little prettier like that. Yeah, very, very pretty. And then we're going to plug in our numbers. Notice that when we plugged in had our givens, our final velocity of mass 1, the first mass of the known mass, was negative 2 meters per second because we said it bounced back. That's where the negative sign comes from. It bounced back. So, plugging all of that in, we get that in order for this to have been true, the unknown mass must have been 27.5 kilograms. So next, we have a billiard ball of a known mass moving to the right, and it hits a billiard ball of the same mass at rest. If, for whatever reason, the first ball continues at 0.5 meters per second toward the right, question is what, maybe it had some overspin. What is the magnitude and direction of the second ball's velocity? Now, as you should have figured out in your labs with the carts, if you collide a cart of the same mass with another cart that is at rest, the first cart will come to a rest and the second cart will go at the same velocity that the first cart had. But what we are saying is that that did not happen in this case. So, well, you know, if you've played billiards before, you can give a ball overspin or underspin to either allow it to keep going or have it bounce back after the collision. So, presumably that's what happened here. So anyway, we have our givens. Same steps as before, sum of pi equals sum of pf, and we have two objects in, two objects out. One of them is initially at rest, so we kill that one to 0. And now we're solving for v2 final. So subtract m1 v1f from both sides, and now we're going to divide both sides by m2 to get v2 final by itself. And yeah, we can factor out our m1 again, making it nice and pretty. And now plug in our givens. And there we go. We get that ball 2 must have continued to the right at 1.5 meters per second. Let's see, that 1.5 plus the 0.5 for ball 1, that equals 2, the initial velocity of ball 1. Well, that makes sense because they both had the same mass. In other words, the initial momentum of ball 1, which was the only one initially moving, must be the same as the total final momentum of ball 1 plus ball 2. And since they have the same mass, the velocities must add up. If they had different masses, that would not have happened. So we say the second billiard ball is going to the right at 1.5 meters per second. So now, here is a bit of a different situation. We have a 100 kilogram cart loaded with 10 bricks that are 5 kilograms each and moving in a straight line with a velocity of 10 meters per second. And then at the same time, 2 bricks are thrown off behind the cart at a velocity of 5 meters per second. And what is the magnitude and direction of the cart's velocity after the 2 bricks are thrown? And here we're assuming that that's going to be 5 meters per second according to people on the ground. But we do need to be very careful with what we're talking about in terms of our masses. Initially, I'm going to say that there's really only one object here. In truth, there are 11 objects, but I don't feel like writing out my conservation of momentum with 11 terms on each side, especially since I know that a whole bunch of them are going to combine anyway, which means things are going to factor out. So instead, I'm going to say that initially I have one object of a certain mass, the mass of the cart plus the mass of 10 bricks, which turns out to be 150 kilograms when you add them all together, going at a known initial speed. This works because they're all going at the same initial speed in the same direction. And at the end, we have basically 2 separate objects. We have the cart plus 8 bricks that are left over, and then we have the 2 bricks that have been thrown off at that known velocity. And notice that's a negative because they were thrown backward. So just kind of a summary again, we have one object initially, which is the cart plus 10 bricks, and at the end we have 2 objects. One of those is the cart plus remaining 8 bricks, which are all going at the same velocity, which we're trying to find out, and the other object is the 2 bricks, which are also going at a same different velocity, which we already know. So those are our givens. Now that we figured those out, it's the same problem as before. Sum of pi equals sum of pf. Again, I'm claiming one object initially, so just p initial, and that's p1 final plus p2 final, because of the right side of conservation of momentum. Every one of our p's is an mv, and we're trying to figure out what v1 final is, the mass of the cart plus 8 bricks at the end. So what we're doing is we're trying to get that term by itself. So we subtract off this annoying M2F, V2F term and get that by itself. And then we're going to divide both sides by M1 final. Notice in this case, nothing cute cancels out or factors out in a nice way because these are all different masses now, but it worked the same way as before. We plug in our givens, and, well, we can cancel kilograms, I guess, but the numbers are different. So working out the numbers, you find that the final velocity of the cart plus 8 bricks after throwing 2 behind must be 11.1 meters per second. And I should add that this is all in the reference frame of the ground. In other words, somebody viewing this from the ground as opposed to somebody viewing it from the cart. In that case, it would be different. If we had done it according to somebody from the cart, the initial momentum actually would have been 0, but then we would have had to shift back to the ground reference frame at the end. And in non-AP physics, we're not going to worry about shifting reference frames. So next problem. Here we have a 5 kilogram object at rest suddenly exploding and being torn into 2 pieces because of that. So a 4 kilogram piece goes at velocity 50 meters per second to the right. Question is, what's the magnitude and direction of the velocity of the other piece? So this is very closely related to our problem with the man on the pond, frictionless pond, starting at rest and throwing a bowling ball. Now, what you could do, you could, if you wanted to, solve it exactly the same way and just say that there are 2 pieces at the beginning, both at rest, and 2 pieces at the end, both at rest. In fact, we're going to do it a little bit differently. We're going to say that there's simply 1 piece at the end and another piece at the end, each of different masses. And we're not even going to worry about what's going on at the beginning. We're just going to say that the momentum at the beginning is 0, because nothing's moving at the beginning. So there are our givens. There's our conservation of momentum. And now we have set the left side to 0. In fact, we could have just set this to 0 initially without even writing it out like this, and then just said 0 equals P1F plus P2F. Each one of those P's is an MV, again, with appropriate subscripts. And we are trying to solve for the final velocity, V2F, of the 1 kilogram piece. So just isolating for that, just using our algebra skills and plugging in our numbers. Again, the kilograms cancel, and you get negative 200 meters per second. So one object flies forward at 50 meters per second, the other goes backward at 200 meters per second. So we say the other piece flew off toward the left at 200 meters per second if the first piece started off toward the right at 50 meters per second. Now, does this make sense? Well, initially, we know that we had 0 momentum, which means we must have 0 momentum at the end. Well, 4 times plus 50 is plus 200. The other 1 times minus 200 is minus 200. And those units in each case were kilogram meters per second. And when you add those together, they do indeed cancel. So our total final momentum is 0 as expected. So next, our last problem. A 65 kilogram person is holding a rock and standing still on a frictionless surface. Ooh, does this sound familiar? If the person can throw the rock, not rocket, at 25 meters per second, what mass of rock must be required in order to give the person a speed of 1.5 meters per second on this frictionless surface? And what average force did the person exert on the rock if the time of the push during the throw is 0.45 seconds? So, as before, we write our givens. Both initial velocities are 0, and we're saying that the rock is object 2 and the person is object 1, and we want to know what mass of rock is needed in order to make this occur. So, here's where we stand so far. And as before, we do conservation of momentum. And 2 objects in, 2 objects out, but initially they're both not moving, so we have 0. And solving for the unknown mass of the rock, we get 3.9 kilograms. That's an 8-pound rock. So, in truth, this is an unrealistic situation. Nobody can throw an 8-pound rock at 25 meters per second, which is about 55 miles per hour. That's just not going to happen. But we're pretending. So the question now is, what kind of average force would be necessary for this? So here is where we use the impulse momentum theorem, the idea that just as an object's final energy is equal to its initial energy plus the work done. Well, here, an object's final momentum is equal to its initial momentum plus the impulse acted upon on it by this external force, where the impulse is force times time. Now, we can also think of this in terms of Newton's second law, where F is equal to change in momentum divided by change in time, or the time interval, that is. In fact, that's actually how we're going to think of it for this problem. So delta t is given to us, that 0.45 seconds. So the change in momentum, well, that's P final minus P initial. Change in anything is final minus initial. That's what change means. And each momentum, again, is mass times velocity with the appropriate subscript. And we can factor out our mass. We're given the final velocity. The initial velocity was 0 because the rock initially started at rest. So now we plug in our givens. And when you get all that out, you get 220 newtons. So that is the force exerted on this rock. So hopefully everybody found this useful, and if you have any questions, please let me know.